Acceleration concept practice. We are starting off here with a car. And here's the motion of the car all plotted out. We are going to discuss it in pieces. So, the car. T equals 0. We're talking about the time. So the stopwatch would look like that. 0 at time equals 0. D equals 0. That's your displacement. That delta D, displacement. That's also 0. Okay? Meters per second. Meters per second measures velocity. Our velocity is also 0 at time 0. Okay? 1 second later. Okay? So 1 second later. The displacement is 5 meters per second, and now the velocity is 10 meters per second. So it moved a total of 5 meters, and it increases velocity to 10 meters per second. During the next second, at 2 seconds, when the stopwatch says 2 seconds, it has now traveled 20 meters from the reference point, and it has a velocity of 20 meters per second. All right, at 3 seconds, it's now going 30 meters per second velocity, and it has traveled a total of 45 meters. And then in the last second, velocity 4 seconds, velocity 4 meters per second, displacement of 80 meters. Take all of that data and put it into the data table. So, one data piece at a time, starting back with 0. When time is 0, displacement 0, velocity is 0. When time is 1 second, displacement is 5, velocity is 10. When time is 2, displacement is 20, velocity is 20. At time 3 seconds, displacement is 45, velocity is 30. And in the last second, displacement's 80, velocity is 40. All right, now we are going to graph the information. It's easier to graph it once we now have it in a data table. First, we're going to do a displacement versus time graph. So variable on the x-axis is time. Time in seconds. We're going to scale that out. We need to go from 0 to 4. So 0, skip a line 1, skip a line 2, skip a line 3, skip a line 4. Now, displacement, we need to get from 0 all the way to 80. Label the y-axis displacement in meters. Starting at 0, we need to get all the way to 80, so go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Now plot the points. So we are going to ignore the velocity column. We're just doing time and displacement. First dot, 0, 0. Next dot, time 1 second, displacement 5, right there between the 0 and the 10. At 2 seconds, it's 20. At 3 seconds, it's 45. And at 4 seconds, it's 80. Connect the dots. And now we have the graph. That graph, we have yet to see that graph. So displacement versus time graph, so far we've only seen them linear. That is not a linear graph. That's not a straight line. It's curved. But let's go back up to the car. What is the car doing? Describe the motion of that car. In one word, describe the movement of that car. Well, the car is accelerating. Okay, so the car is accelerating. Acceleration means that you're going faster and faster. Well, let's look at the slope. Okay, because we know in a displacement versus time graph that the slope is equal to the velocity. Okay, slope equals the velocity in displacement versus time graph. Well, we've got just a little bit of slope here, so we've just got a little bit of velocity. It's going slow. Here, it's going a little bit faster, so it's gotten a little bit faster. And now it's steeper, so it's even a little bit faster, and now it's even steeper, so it's even faster. So it's going faster and faster and faster and faster. It's accelerating. So in a displacement versus time graph, if the graph is curved, the object is accelerating. The velocity is changing. All right, let's look at a velocity versus time graph. Let's graph it. Time on the x-axis. Scale it out the same way. 0, skip a line 1, skip a line 2, skip a line 3, skip a line 4. Y-axis. We need to get velocity from 0 to 40. So we can scale it a little bit more. Sorry, label it velocity in meters per second. All right, let's go with this. 0, go by 5s. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay? So we've scaled it. Now plot the points and connect the dots. First point, so we're looking at velocity and time. We need to ignore displacement. So first point, 0, 0. Second point, time 1, velocity 10. Time 2, velocity 20. Time 3, velocity 30. Time 4, velocity 40. And connect the dots. In this one, we now do get a straight line. Okay? But we know the car is accelerating. We've already established that. So in a velocity versus time graph, the slope tells us the acceleration of the object, which you will discover more as we continue with this worksheet. Next section, we have the motorcycle. I want you, now that you have had a chance to practice with this formula, okay, acceleration, final velocity minus initial velocity divided by the change in time, I want you to calculate the acceleration of this motorcycle. So, you need to find the final velocity, looking at the data. Find the initial velocity, looking at the data. Find the time it took for the trip, and then plug them in. So, final velocity, meters per second, measuring velocity. This one's at the end. Final velocity, 28 meters per second. Initial velocity, the starting velocity, well, that's over here. That's the 0 meters per second. The time it took to get from 0 to 28 meters per second, it took 4 seconds. That's our change in time. So plug all those values in. Acceleration is the question. Plug those values in. Final velocity 28 minus initial velocity 0 divided by 4 seconds. 28 minus 0 is 28, divided by 4 is 7. Units for acceleration, meters per second squared. So we used the formula, we got our answer. Awesome. Now take a look at this for just a moment. Notice our velocities. 0 to 7, it increased by 7 meters per second. And that happened from 0 to 1 seconds. From 1 to 2 seconds, the velocity increased from 7 to 14. It increased by another 7 meters per second. From 2 to 3 seconds, the velocity increased from 14 to 21. Yet another 7 meters per second. From 3 to 4 seconds, the velocity again increased by 7 meters per second. So 7 meters per second increase every second, 7 meters per second, 7 meters per second squared, that's our acceleration. So with that knowledge, go back up to the car without using the formula. Do not use the formula. Just observe. What is the acceleration of the car? See the pattern. The velocity increased by 10, by 10, by 10, by 10. The velocity is increasing by 10 every time. The acceleration is 10 meters per second squared. All right, to the back side. We have data table, we've got graphs. I want you to take that data. I want you to graph that data. And I want you to pause this video until you have completed that task. All right. Let's check your answer. All right. So plotting the points. We are looking at displacement versus time. Displacement and time. I'm going to cover up velocity so don't get confused. At time 0, displacement's 10. At time of 0, displacement's 10. At time 1 second, displacement's 11.5. So just a little bit above that. At 2 seconds, it's 16. A little bit above the 15. At 3 seconds, it's 23.5. So they're between 20 and the 25, a little closer to 25. And then at 4 seconds, at 34, just below the 35 there. Connect your dots, and notice you get a curve. So, if a displacement versus time graph, if the graph is curved, we just saw that. Can you describe the movement of the object just by reading the displacement versus time graph? Why, yes. The object is accelerating. All right, let's go to the velocity versus time graph. All right, let's plot out those points. Let's cover the displacement. We don't want to use that. So first plot, 0, 0. At time 0, the velocity was 0. At 1 second, the velocity was 3, halfway between the 2 and 4. At 2 seconds, the velocity was 6. At 3 seconds, the velocity was 9, halfway between the 8 and the 10. And at 4 seconds, the velocity was 12. Connect the dots. There you go. We have a straight line linear graph for velocity versus time. A linear graph for velocity versus time tells us that we have a constant constant acceleration. Because the slope in velocity versus time graph tells you the acceleration. If it's linear, that tells us that it's constant. Okay, here the velocity is not constant because that's what you get when in a displacement versus time graph, the slope tells you the velocity. The velocity is constantly changing, therefore we get a curve. So, calculate the acceleration of the object twice using both these formulas to show your work. So, if I want to calculate a slope, this slope is constantly changing. So can I calculate that slope? Not using rise over run, but this is a single slope. So we're going to use this graph to calculate the slope, rise over run. So rise, let's pick a point. I'm going to say we're going to pick that point and that point. So for the rise, how much do I rise? How much do I go up on the y-axis? We go up 6. The rise is 6. How far am I going to run? 2. 6 divided by 2 is 3. Okay? Over here, to acceleration. Final velocity minus initial velocity versus change of time. All right, so my final velocity is that right there, which is 12. My initial velocity times 0 velocity 0. How much time did it take for it to get from 0 to 12? It took 4 seconds. So plugging in those numbers, 12 minus 0 divided by 4. 12 minus 0 is 12. 12 divided by 4 equals 3. Acceleration meters per second squared. This 6 was meters per second. That's seconds, meters per second squared. We get the same value. This proves to you that the slope of a velocity versus time graph demonstrates the acceleration. Calculates the acceleration. All right. Last problem. I really want you to try this on your own. Try and get through the whole thing all by yourself before you watch this. So pause the video now until you've attempted this entire section, final section. The first thing we need to do is we have this motorcycle with all of this data. We've got to get all of this data into the data table. So the only way to do that is to very carefully pay attention to the units of measure. So here we have seconds, 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 seconds. Seconds measures time. And then we have meters, 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 and meters, and meters measures displacement. And then last of all, we have meters per second, meters per second, meters per second, meters per second, measuring velocity. So we want to enter that data accordingly. So when the time is 0, the displacement is 0, the velocity is 48. When the time is 1 second, the displacement is 42, and the velocity is 36. When the time is 2 seconds, the displacement is 72, and the velocity is 24. At 3 seconds, displacement is 90, velocity is 12. At 4 seconds, displacement is 96, velocity is 0. You have now entered your data. Now that you have your data entered, I want you to pause and graph that data. Let's check your graphs. All right, so our first graph is the displacement versus time. So we want to hide the velocity for right now, okay? So emphasize this. We are talking about your time and your displacement. That's what we're graphing here. So first dot, 0, 0. Next dot, 1 second, 42, just above the 40. 2, 72, just above the 70. 3, 90, right on the 90. And 4, 96, halfway between that 100 and 90. And then connect the dots. You should notice you get a curve. Velocity versus time. Okay? So again, time on the x-axis, but now we have velocity on our y-axis. So we're going to hide displacement column so we don't get distracted by it. Okay? At time 0, our velocity is 48, so just below the 50. At time 1 second, our velocity is 36, so about halfway between the 30 and the 40. A little bit above halfway. At 2 seconds, times 24, so a little bit below halfway between the 20 and the 30. At 3 seconds, it's 12, so just a little bit above the 10. And at 4 seconds, it's 0, right there on the axes. Straight line, connect the dots. You can hopefully see that that's linear. All you gotta do, connect your dots. There you go. So we have now both of those graphs. Now, hopefully you're doing the it looks a little weird. If you compare it to the other graphs, you've got the curve, but it's curving differently. And you have the linear, but it's a negative slope rather than a positive slope. So the key to this is recognizing the importance of this is still an acceleration, but it's a negative acceleration. So the object is decelerating. Okay? So to calculate that, go over here. We're going to use the velocity versus time graph to do this. We want the slope of the velocity versus time graph. So rise over run. Now you're probably looking at this like, oh, those numbers. Pick a number, write down what it was, 36. Okay? Pick another number. Let's do this one, 0. Okay? So the rise was 36, but it's going down, a negative 36. The run, to get from there to there, 4 minus 1 is 3. 36 divided by 3, negative 36 divided by 3 is negative 12 meters per second squared. Negative. A negative acceleration is deceleration. All right, let's go with this one. Final velocity, initial velocity. So our final velocity, well, the final velocity was 0. Our initial velocity was the 48. All right, that 48 right there, that was our initial velocity. The amount of time it took, well, that again, 4 seconds, 0 to 4 seconds. Let's plug those values in. Final velocity is 0. Initial velocity is 48. Divided by the amount of time it took to get from 0 to 48 to 0, 4 seconds. 0 minus 48 is negative 48. 48 divided by 4 is 12, so negative 12 meters per second squared. It's decelerating by 12 meters per second every second, so 12 meters per second squared. And there's that worksheet.